Hello, I'm Adam Chen. I'm here to present our work on using commutativity to do declarative multi-core programming. And to kind of motivate our work, I'd like to talk about how we're kind of at the limit for single core performance. So to get additional performance, chip manufacturers add more cores to CPUs. But as we know, to actually get benefit from this, we have to do concurrent or multi-core programming, which is quite difficult. It's difficult to teach people how to do, and even for people who have done it for a while, bugs can slip through, and when this happens, the bugs are often non-deterministic and hard to fix. So kind of the dream is to have a serial program and have a compiler generate concurrent code automatically. But once again, the field of parallelizing compilers is well known to be a difficult problem. But I would like to focus on kind of a case where there's been a little bit of success. This snippet is from the OpenMP for C++, and we're able to to parallelize this for loop in part because it's labeled as a reduction, doing a sum. And these operations are parallelizable in part due to the algebraic properties of addition, and namely commutativity, associativity. And we'd like to focus on the commutativity aspect because it's well known to be an enabler of concurrency. And this goes back to work in databases and previous work in parallelizing compilers. But the problem we're kind of looking at is, what if the operations that we would like to parallelize don't always commute? Is there anything we can do in that case? And to kind of look into this, let's look at a little bit more involved of an example. So here we're assuming that these long funs are long-running pure computations. And so you can see at the start, we're doing this long computation to get some return value x, and then we're going to update the value of c based on x squared. And then we're going to take a branch based on this updated value of c and potentially some other program variable y to do different behaviors. On one side, we're going to further update the value of c and call another long function. Or if we take the else branch, we're going to do a completely different long function. And what we kind of want to think about here is that if these long functions are the bulk of our work, then we would like to run the first invocation and whichever one happens to be in the branch that we take in parallel. So let's forget safety for just a second. What if we were to split the program up in the middle here? So this would be very nice if we could actually parallelize the program like this, because we isolate the first long function in the first part and whichever one that ends up happening in the second part. So this is our kind of core idea. We would like to do this, but of course, data dependencies stop us from doing this safely in a naive way. So most notably, we update the value of c on the second line, and we immediately check it on the third line. And even if we were to split it one statement higher, we don't really get rid of that fundamental problem that we have this update to x and this read of x on the second line. So our main idea is that we have these data dependencies, but maybe if we find some situations where these blocks commute, we can avoid some of these dependencies. So for this example, let's consider the case where c is greater than 0 initially. Then we know that, let's just say without loss of generality, that y is less than 0. We know that after the second line, c is going to remain greater than 0 because x squared is going to be non-negative here. So if we were going to take that first branch, we're going to go down that first branch, just as in the case where if we execute the second block first, we would still take that first branch. And then the result here is we're going to have these two updates on c, which commute due to the algebraic properties of addition. So the idea here is that we propose a new language construct, which is going to allow the programmer to express conditional sequential commutativity. So by this, we mean conditional in the sense of they don't always commute, but if some, say, predicate holds true, they will. And sequential in that we're only reasoning about discretely the first block happening and then the second, or the second and the first, and not interleavings. For the remainder of this talk, we're going to call these blocks fragments, just to avoid confusion with other notation. And other benefits of thinking this way is that we would like our verification tools to only reason sequentially as well, and yet we'd still like to get benefits from running these in parallel. So the idea kind of looks like this, where we're going to check the commutativity condition initially. And if it doesn't hold, we go to this right side and just run the code sequentially. But if it does hold, then we would like to fork and run these two fragments in parallel. And clearly, we don't get this for free. There are a few things we need to do. So first, this commute statement is a new construct, so we're going to have to give some kind of formal semantics to it. We're going to have to ensure that there's some safety property that allows us to just fork and run these in parallel, and we might have to do some kind of blocking to enforce that. We need to talk about these commutativity conditions, how we can get them and what it means for them to be correct. And then we'd just like to verify that indeed we can get speed up as these long functions get longer. So let's start with specifying the semantics of the commute statement. So kind of to keep the eye on the goal, we have this program S, and we'd like to have two notions. One notion of running it sequentially that we can just reason about and write pretty easily, and then one notion of what it means to run that program in a parallel way. And so we call our parallelization sound when we get this equivalence of semantics between the sequential view of the program and the parallel view of the program. That way, the programmer only... Sorry, microphone issues. I'll just carry this. That way, the programmer only ever has to reason about the sequential side of the program, which is easier, and then just let the analysis and compiler take care of that parallel side. So let's define what these seek and par subtitles or subscripts mean. So let's just start by briefly outlining our approach to giving our language a semantics. We're just using the approach of contextual semantics. So every program can be divided into a regex and a context. We just give some standard redexes and add these redexes for our commute statement. And we're going to have these reductions on redexes. These are pretty standard. We're just going for a variable, we just look it up. For a Boolean or for a binary operation between constants, we just evaluate that. And for an assignment of a constant, we're just going to update the state. And we're going to add this regex or this reduction for commute false when that commutativity condition does not hold. We just want the two statements to execute in sequential composition, the right-hand side of that diagram for before. Then we just add a pretty standard small step semantics rule that allows us to reduce programs. And the important thing to note here is I haven't provided a reduction for commute true. And why is that? So the reason is we want these two different notions of how we're running a program. To differentiate between them, all we're going to do is going to give different semantics for commute true. So in the sequential case, this is pretty immediate. We just want this to be our straight line code program. So all we have to do is reduce the commute true statement to a sequential composition. For the parallel version, we introduce a little bit of machinery. We're using the approach of configurations. So a configuration is defined to either be, like we had before, a statement and a local state, or it can be, you can think of this as a notion of forking. You have a left fork, a right fork, a statement that is the remainder of the program to be executed after the join, and a shared state. So then we can define our commute true reduction as just creating a fork. And so, for example, we can apply our reduction rules either on the left or on the right. So for example, when we have this commute statement, assuming that it takes a parallel branch, we'll get an interleaved execution. So to kind of sum up this part, we have these sequential semantics, seek. We have these parallel semantics, par. We're going to view every program as a state function. So we have this associated function s sub seek and this associated function s sub par, and we want these to be equal. That is to say that for every starting state, we're going to end in the same ending state no matter which one of these two we use. Notably, the sequential semantics are deterministic, so this is also equivalent to saying that the parallel semantics behave in a deterministic way. Now, how do we guarantee this condition? So normally, when you want some kind of condition of parallel semantics behaving in a deterministic way, we would use something like serializability. So the question is, can we use a pretty stock definition of serializability? Recall that serializability is just defined as an equivalence to a serial trace. So when we have some interleaved execution, we can reorder the reductions to be able to get serial ordering. And I'm going to show you this example that shows that serializability in and of itself is not quite sufficient. So consider a few of these traces. We're going to execute F1 and then F2, noting that no matter which one of those two executes first, we're going to get X be 0 at the end of that. And then we're going to check this if condition. So if we take this left nesting in the outer commute block, no matter which one we do of F2 or F1, we're going to end up with X equals 0. And then when we look into F3, we get that if condition is going to see false. Conversely, if we did the right branch of that outer commute statement, we're going to also get that to be false because X is set to 1 beforehand. But now consider this execution, where we execute F2 to double X, thus making X2, then F3 to check if X is greater than or equal to 2. And in this case, it will follow the if condition. And we don't want this to occur because when we're reasoning about commutativity of blocks in a sequential sense, we think of each block executing to completion before the other one happens. And so what we need is actually a strengthening of serializability, which we call scope serializability, which is defined in terms of equivalence to scope serial traces, much like serializability is. The additional restriction is in what ordering of threads are allowed in that serial trace. So we can think of these commute blocks as nodes in, say, a tree. And we're allowed to swap the order, temporally speaking, of its children, but we can't put this F3 child in between the F1 and the F2. So our way to solve this is to label all the transitions associated with a fragment based on where that fragment is. So for example, you get to the LL fragment by going to the left on the outer nesting and then going to the left again on the inner nesting. And this is just a way to uniquely define or uniquely identify which fragment a particular transition in this execution of the program comes from. Then we just require that all the fragments with complementary prefixes, which is to say that one of them is something ending in R and then the other one is the exact same thing ending in L. In this case, it's pretty simple. So we would just have nothing followed by R and nothing followed by L, or R and L. So we require these fragments with complementary prefixes to be serial with respect to each other. So we would disallow this top, we would not count this top execution as serial execution because this R is in between transitions from that have L in the prefix. Whereas we are going to allow this last one because the R is to one side of all of the transitions that have an L as their first label. And we need to be able to enforce this condition. And of course, one common way to do so would be to synthesize locks. And there's a lot of works on synthesizing locks to ensure serializability that could be applied here. However, we argue that a lot of these previous techniques are suited to more like massively multi-core or ADT methods, those kinds of settings. And in our general purpose programming language setting where we have this pairwise flavor, we're just going to end up mutexing these two fragments a lot. So we present a few techniques that use commutativity information to try and achieve shorter windows of locking. And to kind of just show that this is possible, I want to start with naive locking, where we just say we identify the shared variables between the two fragments, and we just want to lock on the entire critical section that touches those shared variables. And for our example here, this actually works out quite well. So the only shared variable is C. So in the first fragment, we just have to lock on that update to C. And in the second fragment, we can start by locking on the beginning, and then if we take the if branch, we'll unlock after we update C. And in the else branch, we know that we don't use C at all, so we can immediately unlock. And we actually retain a lot of the gains that we would get here from naively parallelizing it, because the long functions fall outside of these locks. So this example shows that even with naive locking, it may be possible that we still get large gains from parallelization. And it also goes to show that it's always possible to enforce scope serializability. However, we present a slightly more sophisticated method where the idea is that since we have this commutativity condition that we can assume is true and leads to commutativity between the two fragments, we can weaken some of the data dependencies that would otherwise occur from the first fragment to the second fragment. So we can just identify the critical section for each fragment, and using just a traditional data flow analysis, separate the things that have to happen before the critical section and then after the critical section, and then only lock on the critical section. The advantage here being that we have fewer dependencies than normal that would otherwise exist from the first to second fragment. And there's a few additional details here, like we have to snapshot the state, but that's all in the paper. And once we have the scope serializability, we can apply this theorem that if every commutativity condition in S is valid and S is scope serializable, that's to say all traces of S are scope serializable, then the parallel semantics will equal the sequential semantics. And we haven't really discussed what this if every commutativity condition in S is valid means. So let's do that. So I want to consider that before you execute this commute statement, you're going to be in some state sigma naught. And if you do the sequential ordering, doing the first fragment and the second fragment, you're following the top and the right side of this diagram to end up at sigma 1, 2. However, as the name commutativity implies, we want to think about swapping the order of these two fragments. So instead, we can think about following the left and bottom edge of this diagram to do the second fragment and then the first fragment to end up at sigma 2, 1. Now, what we mean when we say a commutativity condition phi is valid or correct is that if it holds in that initial state sigma naught, then we know that sigma 1, 2 and sigma 2, 1 should be equivalent. Or another way to think about it is that we could non-deterministically pick which fragment we execute first, and they'll appear to behave deterministically. And there's some existing work on inferring and verifying commutativity conditions, but this work is done on logical ADTs. So we had to come up with a way to translate our commute statements to logical ADT specifications. The way we're modeling this is that we want to turn our statement into an ADT where the state is just the program state, and we have two methods, one corresponding to each of the fragments. And this requires coming up with a specification for the semantics of our fragments as logical SMT formulas. And the best way to illustrate how we do this is with an example. So let's consider this example where we increment X, and then we have a commute statement that just does some simple assignments. So when we start our translation, we're going to just initialize this ID map, which is going to map all the names of our program variables to what you can think of as a current state of that variable during the translation. So they're all going to start at the pre-state of the variable in our method specification. Now, when we translate this first assignment, we're just going to create, say, a new name for this variable, say x1, and we're going to just translate the right side of that expression and assign that value, or create a local binding for that value. So you can see here we have let x1 be x pre plus 1, and then the body of that let statement is just going to be the translation of the tail, which is this commute statement. Now, the cool thing about translating the commute statement is that by assumption, we have that it doesn't matter which order we pick the statements to execute in. So we can just pick an arbitrary order. Let's just use the order that they're written in, so we can translate this commute into however we would translate the sequential composition of these two statements, which we already know how to do assignment. We're just going to create a binding for y and let it be 2, and create a binding for z and let it be 3. And then since there's nothing else left to translate, then we denote that with a skip. And all the skip is that it's going to assert that the post condition of the variable is going to be whatever the most recent version of that variable is in the ID map. So in this case, the entire thing would translate to let x1 be x3 plus 1. That's the assignment statement. And then the commute statement is let y1 be 2 and let z1 be 3. And then to just equate all the post conditions with the most recent version of the variables, we have the conjunction of the post state of x is equal to x1, the post state of y is y1, and the post state of z is z1. And you might be thinking, what about loops? So indeed, loops are a little bit difficult for this kind of translation. So currently, we assume that one has an oracle to create a loop summary. That is to say, a way to express all of the mutations that occur within inside the loop. And in practice, we're currently using a combination of manual inspection and previous tools in loop summary synthesis. Specifically, we point towards Corn. And then we're able to insert this summary versus via assume and havoc statements. So once we have this translation to logic, we take our commute statement, we translate it to the logical ADT specification, we run it through this tool called Servoit2, which does commutativity synthesis for logical ADT specifications. And what we get out is a commutativity condition that is guaranteed to be valid. We also get a non-commutativity condition, but we don't use that. And sometimes it's practical for a programmer to want to use their own commutativity condition, either because synthesis is difficult or because there's a simpler condition that covers most cases. In this case, we can use the exact same translation of logic and the exact same tool to verify that this condition is correct in the sense that we presented before that square diagram. And all of this is implemented in the Veracity language, which is a C-like language with support for ADTs like arrays and hash tables. It's our research language. It's implemented in Multicore OOPSLA, and currently it's implemented as an interpreter. We'd like to turn into a compiler in the near future because we believe that would allow us to do more fine-grained locking. On the back end, we can connect with a variety of SMT solvers to be able to synthesize, or rather confer and verify commutativity conditions for our commute statements. And all of these examples are with our Veracity artifact, and they can be executed. And so finally, the evaluation. So there's no real canonical benchmark set for the commutativity conditions of programs. So thus far, the work has mostly been focused on ADTs. So we created our own set of benchmark programs, making sure to include linear integer arithmetic, arrays and maps, some nonlinear arithmetic, vector operations, and loops instrumented with assume and havoc. And we can see that for most of our examples, indeed, as we vary the size of those long functions that you see or saw, we do end up getting speed up. And the long-running example we've been using through this talk is this calc example, which follows this trend line here. And we also looked at if we could practically synthesize commutativity conditions for most of our programs. And you can see for the vast majority of these, we get a pretty readable condition in just a few seconds. And there are a few with either very long, hard to read conditions, or they take a long time to the point of timeout, or both. And unfortunately, our calc example is one of these. The ... just indicate that there are a lot of disjuncts that we've excluded for the sake of clarity. And this is where that programmer specified condition comes in, because by inspection, we could see that that calc example commutes in the case where C is greater than 0. So as testers, we plug in C is greater than 0, and we found that our tool can verify this as a correct condition in just a few milliseconds. So I'd like to thank Parisa, Eric, and Jared for also working on Veracity. And to kind of re-summarize, we're programming with conditional commutativity to be able to obtain speed up that we'd expect from parallelization while only having to reason about this sequential commutativity. We presented the correctness condition for being able to do this, which is scope serializability, and we showed that we can synthesize commutativity conditions for a few practical programs. Here's the link to the artifact, and you're also welcome to read our technical report or get our docker from veracitylang.org.
So what's the semantic for your integers? Do you have unlimited integers or do they overflow? Because if they overflow, your first example don't commute.
Yeah, so we just assumed that our integers were mathematical integers. Admittedly, we were taking some abstractions for granted for being away from, say, bare metal.
Mm-hmm. So, in a methodological perspective, how do you discover that the nested commute don't commute that well? Like, it's an interesting, thought-provoking fact. And I wonder, how do you discover it? Was like some related work already noticed? Did you discover it in this work?
I can't really recall the exact moment that we would discover it, but I can definitely say that in trying to prove our theorem, it becomes clear that serializability is insufficient.
Other questions? In that case, let's thank the speaker again.